Hi everyone, and welcome to a gentle intro to large language models and their real-world applications. I'm a software engineer at Cohere. I work on machine learning, serving, and productionizing models that are large language models. I'm going to start off with a very simple example to kind of get you all into the ropes of what large language models are and how easily you interact with them on a daily basis. When you go to Google and you try to search for something, say you're trying to understand how Siri technologies work, right? Like how does Siri work underlying to its functionalities? You go and type like Siri, and before you're even finishing your entire second word, it's already predicting you the next word. Right now, there's a competition going on between your keyboard and Google to see which of these is correctly what you're looking for. And then when you actually end up searching for that query, you get a response that looks something like this, and you see like a small excerpt over there that describes kind of what your answer should be. So you don't have to actually go and open the article; it's just summarized right there. And the question I like to ask people is the fact that when you click on that, you see this highlighted text that pops up to you. Which part of this actually ends up using large language models or NLP in general? So if you guys think it's one, can you raise your hand and give me a show of who all think that? All right, a couple of people. How many of you all think two is a part of it? All right, a few or more. And then three. All right, so we don't have strong confirmation thinking like any of these are largely using a lot of language tasks. So I'll tell you that all three are actually using language processing in some form or the other. And the first one is basically a form called predictive text, where it tries to say predict the next word, right? And this is one of the fairly common use cases for it. We had older technologies, and now we have more modern, more powerful machines and systems that actually focus and build much more accurate predictions to what you're going to type. And the second part as well, again, is natural language processing. That part generally ends up being a form of generated text that is a summary of like the concise answer of what you're looking for. And in many ways, it's going to save your time. And the last part, again, is the fact that it highlights that specific text and it gives you exactly what you're looking for, but points it not just to a specific summary, but a website that actually contains those exact lines. And I'd argue there's a step in the middle called 1.5, which is sort of the most important. And this is kind of the foundation of how semantic search and how Google search and a lot of these search engines function nowadays. So like I said, auto-completing is predicting the next word. Semantic search is basically finding correct articles with the correct content from a huge repository of content, and then text summarization, which distills that, and then actually question answering. If you look into semantic search, it's actually one of the deeper and more well-seated parts of large language models and their abilities to get you the right content. And it's been around for a while, the term semantic search, but the ability and the power of it is growing more rapidly as we get more and more powerful models. Another example of what large language models are capable of is response selection. If you try to write an email and you're sending it to someone, when they get that email, they have options of how to respond to it. And you'll see these like quick, neat summaries that come in Gmail or any other email client. You'd see they're short, concise, and often pretty accurate to what you should be doing. So yeah, these are the different areas of applications of in real worlds for language processing tasks. And a lot of these end up having some form of large language model at the basis of them nowadays. And to take a segue again, just from purely large language models and their vanilla applications, there are a bunch of use cases where you end up taking these models and you use them in conjunction with more powerful models or technologies to build really powerful applications. One of them, for example, is vision. If you look at image captioning, you see like really old existing models back from 2015 and 2014, where you would have like a sentence description of an image. Another example would be visual question answering, and I'll dive into that later. But think of it as like you have an image, you ask the model a question, it understands the intent and the direction of the question, and then tries to answer it based on what it's understood. So it's using like some vision-centric tasks and information in conjunction with the language model to kind of get you the answer that you're looking for. And the last part is probably something that all of you are more familiar with nowadays because it's pretty much the hype. It's image generation. You give it a text prompt and it generates a nice image for you, and it can be any form of image you want. It's very flexible. It's currently very trendy, and you see a lot of social media posts about it. Again, there's OCR, and you'd argue why OCR is just language, because you can just recognize characters without knowing the actual language and detect it. But to get a really robust language model, you need to understand not just the exact characters themselves, but in conjunction what they mean. So you can even understand more complicated pieces of text that aren't easily readable, like maybe a handwriting or so on. And there are a bunch of other applications, but the one I'm focusing currently on is captioning. So let's look at this image, for example, and look about how it came back to that summary. Again, this is back from 2015, so like 7 years ago, we were able to do this. And at that point of time, this kind of blew my mind because in my head, I didn't think this was possible for a machine to do as a software engineer until I got to know the power of deep learning and language models in general. So it says a group of people are shopping at an outdoor market and there are many vegetables at the fruit stand. Now, obviously, this might not be what a human describes it to be, but it neatly captures what the exact picture is. And to me, that's great power. There are a bunch of applications that can arise from that. Another really cool example of this would not be just understanding or capturing the image, but getting like a more deeper semantic understanding of it, and then being able to interface with this language model that understands it and have a communication or a visual question answer session with it, right? So DeepMind Flamingo actually came out with this, and you see a picture of Barack Obama. He's a former president of the United States. And then this is a sample conversation that happens in the model, and I'm going to read it out loud because it's kind of tiny on the screen here. So this is a picture of Barack Obama, and he's the former president of the US. That's what the model is telling us. And that's great, right? But clearly there's more going on in this picture. So let's prompt this model. Let's urge it to give us more information. How many people are in this picture? It says, oh, there are 5 people in this picture. And neatly enough, it actually didn't mess up. If you see, there are reflections in there, but it captured that and it was able to say that there are 5 people, and the reflections aren't necessarily people, which is great. And then it asks, where is this picture taken? It says it's taken in a school, which I'm not sure if it's correct, but I'd say school isn't very far off. The next question is, how many mirrors are there? And it's able to detect the objects and even give you answers to them, right? So it's counting objects. So here, there are 2 mirrors in there. And what is the person standing on? If I asked a question like that to you, you'd say which person, but it knows what the center attention is. And it's going to say the person is standing on a rug. Clearly, that's not the person that we're concerned about. We're kind of concerned about the other person on the scale. So we'll tell the model, hey, the person is standing on the scale. And the model is like, okay, you're right. So then you ask it, that's not all. I want to know what he's doing. And he says he's looking at a scale. Great. But now it's coming to the part where this humor is there. And it wasn't obvious to me in the starting, but if you look closely into the picture, you'd see that Obama's foot is pressed on the scale. And then it says it's on the right side of the scale. It's able to understand the relative position of it as well. Even though this model wasn't strictly trained to do this task, it's able to generalize and understand the intricacies of this and even communicate with you effectively. And what is the result of him putting his foot on the right side of the scale? The scale shows a higher weight. And to me, that's funny, right? So is the person on the scale aware of it? You're trying to tell the model that, okay, get deeper into that. And the model is going to tell you, I think he's not aware of it. You ask the model, like, is this humor? Is this funny? Is this why people are laughing? And the model is like, I think so. So clearly, the model isn't perfectly communicating what you want it to, but if you urge it and prompt it, it can get to where you want it to be. And these are like emergent properties in large language models, where they might not immediately do what you want them to, but if you prompt them, if you like push them in the right direction, they can get to where you need them to be. And I'll talk about prompt engineering more in the future, but let's talk about something that's really trending right now. Image generation. There are a bunch of models out there, Stable Diffusion, Dall-E, Image Gen, that actually take in prompts of images, text, and convert that to an image. And this is mind-blowing in itself, because it's able to understand not just the intricacies of it, but to get like a visual image description of it. And this model isn't trained on a specific task. It's trained to like just look at text and generate images, right? But if you look at the examples over here, you can see Kermit the Frog inserted into a bunch of different movies. And it's able to get the aesthetic and the styling of the movie. So if you look at the one on the top left, it's inserting in Star Wars, and the one on the right, it's Blade Runner, and you can see some neon feel of it, right? Like you're getting the Blade Runner kind of the vibe from it. And then you look at the one on the bottom left, and it's Matrix, and you can clearly see he's got like those Neo kind of glasses on, and he's feeling more like he could be a part of the Matrix or trying to escape it. And then the last one is from Spirited Away. So clearly these models are able to capture more context than you could probably do in the past. Another example that you probably would interface with and may or may not use as often is when you're searching for images on one of your cloud platforms that offers you the ability. So this is on Google Photos. One of the really cool applications of it is that it doesn't just look at the picture and tag it immediately. It does OCR, as I mentioned, and then extracts the Elixir part of it in the text, and then tags these images or labels these. So when you look up and you add a content, it's able to like get close semantic tags to it and populate them for you. So you get all these neat, really well-labeled images just by searching for something around there, right? And there's obviously more going on down there with location and that metadata and all those, but you see the crux of it really lies in the power of a language model and the ability for it to capture this information and create it in a form that's indexable, searchable. On the right, again, like can't have pictures without cats, so a cat search gets you that. So, like I said, there are a bunch of really cool use cases of these large language models and the applications of them in the real world that we actually use on a day-to-day basis and we aren't really well aware of. And to me, that blows my mind. They become so ubiquitous in our lives that we take them for granted, and they're getting better and better. So the possibilities of what's going to come in the future is endless. Where else are these really used? We might not all use it, but we're definitely thankful for it. And you can see how it's not just used in tagging or generation, it's used for translation as well. And it's used for like these really smart virtual assistants that don't just understand and your speech and convert it to text, but actually extract information out of it and bring you useful content and act on it based on that. So it's activating on intent, it's activating on your information, it's activating on other content that actually brings you what you want. And to me, that's really cool where they've come in the last 10 years. But what got them here? Say back in 2018, this is around the time where I was in grad school, I ended up actually hearing about BERT and I thought it's really fancy. And then a year later, Google goes out and actually productionizes it. In 1 year, it ships out this revolutionary technology that improves searches drastically. And to a regular user, maybe we didn't feel the difference as much. But as you started working on more complicated queries and started looking for results, you'd see more and more of these results actually end up being what you want. And that's mind-blowing, right? What changed in 20 years where it was using the same technology for 20 years and then changed to using a large language model and boom, searches are better. Search is actually productionized. For 20 years, the software engineers worked on technologies and ways to improve these, and you see a generational leap in a matter of 1 year just by using a large language model. For me, that's mind-blowing. But before I proceed, let me give a huge thank you to Jay, who's actually prepared these slides and who's given a talk similar to this before at PyData London. He's one of the folks at Cohere who actually works and partners with people outside. He helps evangelize and talks about all of these large language models. He has a YouTube channel and he's pretty active, so you should feel free to follow him. And he's got great content out there that you can use to wrap up on large language models. Before I dive in a little deeper on like specific use cases of large language models, I'll give you an example of what we can do to get access to these large language models and play with them and get to know them. So Cohere is the company I work for. We focus ourselves on building NLP SDKs and toolkits that allow people to integrate them into any pipeline without having a strong understanding of NLP or machines that can run this kind of complicated predictions and training. So we train these models and get it out there for you with just a simple API. But before I allow you all to sip the Kool-Aid, let me actually talk about why all of this is of any important to anyone, right? Apart from all the applications you already saw. Some of the use cases that we actually see, not just in the industry, but ourselves sometimes, is that when we're talking to these customer service people and we start a conversation, we don't immediately get a person sometimes. We get like this bot, this AI that actually waits for us to ask a question and directs us in the right way. So sometimes you're not even talking to a human entirely. Sometimes it's entirely a bot and it's able to interface and have a full-fledged conversation with you. It's pretty coherent. It understands almost always what you want it to. So it's getting intent, it's getting what you want, and it's getting information to you out there. All of this is powered through an underlying large language model, which itself replaces entirely like stacks of technologies that combine together to solve these problems. Another really important part, and especially because a lot of people are coming online and you probably have seen this not just on social media but in other forms of the other, is content moderation. And you could use this in different settings, but I use social media as an example, largely because content moderation on social media and other platforms where you have like millions and billions of users are much harder and they're not human interventable, which means that they need to have technologies and solutions and really strong models that understand language to be able to moderate and bring down these content that is either toxic, neutral, or just something that you don't desire for that platform. So how do you actually distinguish or get information out of these? There are different use cases, but one of them would be, say, a classifier. And in general, a classifier can be used to say, is this a positive sample? Does this exhibit the behavior I wanted to? Or is it a negative sample? Is it a cat or a dog or something like that? So it's basically discriminating between two different types of data, and it's going to give you a class label for it. Another use case, as I mentioned before, is semantic search, where you actually search for something and you have like a huge repository of information, and you try to find what closely resembles that. And why is this not the same as just a string lookup, right? Like if I have a search query on Google, why does Google not just run a simple search for those exact words across multiple websites? And the answer to that is semantics. Just because the document contains the words you're looking for doesn't mean it's what you want. It doesn't mean that it's talking about what you're aiming to solve. And that's why PageRank kind of got replaced by BERT and such models like that. And then another use case of these models is pretty neat, is text generation, right? So we've come to a point where these models can actually generate content that is very similar or almost identical to what humans could write, and the quality of these keeps getting better and better. We've seen models like GPT, GPT2, 3, and so on that actually create entire blog posts and articles or even scripts for movies that are very believable, if not faulty sometimes. So let's talk about classification first, taking a step back. Right? I talked about how like you can discriminate between two kinds of text, whether something is toxic or non-toxic. But how is this done? How do we get to that? How does a model understand what it needs to do and what's the starting point? So you can feed in text to a model and you can say that this is class A, class B, kind of have it as a structured problem, train it in a supervised fashion and get this result out, right? So I'd actually argue that in the case of sentiment, as I mentioned before, for toxicity, there is a case where you want to not just detect good intent or bad intent, but neutral intent, and I think that's the difference between academia and industry. A lot of industry right now actually involves you add a neutral or like a non-activated form of this sentiment, largely because language isn't always emotionally charged, and the academia generally focuses on like, is it good or bad, and that's kind of it. Because it's easier to evaluate, and it's also a huge pain to change all of these data sets that were trained purely for these cases. But yeah, another really cool example is that say you buy something for Amazon or Walmart or any of these providers, right? And you want to return it. Before you do a return, you can go to the chatbot and you can say, hey, I want to return something, right? So you might not even use the word return. You can just say something about the fact that like the product I found is faulty, it doesn't have the battery that was supposed to be shipped with it. So it will understand that you might have a complaint with it, and it will try to segregate this into categories of, hey, like, are you complaining about the quality of the product? Do you want to return the product? Or are you saying like it didn't reach you in time, right? So these different categories for classification of returns and so on. But here there are two problems that could actually arise, right? If I got a product that is bad, I want to A, complain about it to make sure other people are given feedback about it and get that information. And B, I also want to return it. So this becomes like now a multi-label classifier, which is different from having multiple classes. This is more about the fact that a single entity can have the ability to belong to multiple sets. And the reason that I distinguish that easily over here visually is by using like those really buttons instead of checkboxes. So in checkboxes, you can select multiple of them and they're all valid answers, but in really buttons, you can only select one of them. Another example is email spam. A lot of you can actually go down to your email and open up your spam folder on your email client and see like bunch of emails that are actually filtered out for you. And sometimes they filter out really good ones, but almost always they filter out the bad ones. And this is kind of a very useful example of how it saves us time from dealing with spam or people trying to hack our emails. Again, I mentioned about toxicity classification, but another really cool example is chatbot intent classification. I already talked about the Amazon example, but this doesn't just limit it to that. Think about having full-fledged conversations with a teacher or something similar to that to kind of get answers to your problems. You can go into this scale and like generate this problem or fine-tune it for any use case. Say you want to know information about PyData, you don't want to look at the schedule. You can actually have a chatbot trained on the entire data set of like the entire talks, and you can ask it questions and it will tell you, hey, this talk is in conference from ABC and so on, which is pretty cool. But we talked about classification, right? And that's one really interesting use case. But what's also really fascinating and probably more exciting to me is representation, which isn't just about discriminating between two things, but also kind of finding a way to encapsulate this information that the model has into a way that's digestible by other people. And how do we really encapsulate text, right? How does the machine understand it? Well, it's binary, right? Well, kind of, sort of, but binary doesn't really encapsulate what you want. You could have That's a tense right there on the top, input it as ASCII, and it looks like that. And that's probably useful for some kinds of use cases, but if you want to really get to the meaning of that sentence, that's not going to get you anywhere. And you can even go to Unicode and capture it like way more different types of things and have all the emojis that you have on your keyboard out there, but it's not going to get you the true deeper insight of what the language is exactly. So yeah, like I said, you can have, without language models, you can have a way to validate your password, and that's great. But if you want to build something really fancy, you want to build applications that leverage the semantics, the language understanding, and the ability for you to get deeper meaning of these texts, you want to use large language models. And one of the common ways to do that is to use the embeddings of these models, which I'll talk about in more detail, and then build things on top of these embeddings. Now, what are embeddings? Well, embeddings are kind of a way for the language model to encapsulate information that it already has, but in a numerical form that can be used for it or even other models down the line. So you can kind of have a vector representation, right? An array of numbers, maybe like 1,000 or maybe 4,000, depending on how you train your model. But it captures, like in these floating point values, it captures meaning. And you can see that how can these numbers capture meaning? And I'll get to that in a bit. But take my word on it that these models can actually encapsulate data in those numbers themselves. For example, you can look at the embeddings of these sentences and say one is similar to the other, right? If one is similar to the other, it means that they're likely talking about the same thing. They have some semantic similarity. An example of that would be, you can ask the model, or you can ask someone, how is it going? And you can ask them, when do you open? Or, hi, how are you? And you realize that, how high are you? Hi, how are you? Are kind similar. That was not intentional. To this specific thing. And you realize that when do you open is not really the same question as how it's going, at least not in the English language. And then that's coming to a point, right? Like when you get similarity and when you get certain things that are closer in meaning to the other, you can get to a point where you're able to effectively visualize these embeddings by reducing them from thousands to maybe like 2 dimensions, right? And be able to like get insights out of this. An example of this would be like to take all the tweets you've ever written, get the embeddings of those and visualize them. And you'd see that some of those tweets you're complaining about maybe like subway train that you just missed, or you're complaining about the fact that there's too much noise in ambulance in New York, or you're complaining about how beautiful Central Park is, how you're really missing it out because you're stuck in your room because of COVID. So all of these things can be clustered differently, and you'd see them drawing closer and closer to each other if they have semantic meaning, and that is useful information to actually get you to where you want to be. But how do you go about this, right? How do you extract these data and where do you use this? Like I said, you can use these to create semantic classifiers that actually take in like different extracted vector representations and train like sentiment for it. So you can get like a positive, negative, or neutral sentiment. And you can do this very easily with other large language models and get decent performance. But if you really want to capture complicated pieces of text and get a really highly performing classifier, you want to get to large language models. I've talked about large language models, but I wanted to take a step back and look about the history of it. So like, how was this done prior to large language models, and why are large language models important? In the past, you'd use these scikit-learn functions and modules called count vectorizer or TF-IDF, which is basically a way to say if a specific term has a higher frequency, it's probably less important. And that's a way for you to understand which of these terms have more meaning or what context they're used in or how they're represented. So obviously you can get a vector representation by just using these counts or that additive frequency and get that to be trained through a logistic regression classifier, but you get a very subpar performance in most cases. And in those cases, I recommend using a large language model to actually extract these embeddings instead of TF-IDF or a count vectorizer, and then pass them onto this model. In fact, you can have tens of hundreds of thousands of examples, extract embeddings, and really train very powerful classifiers. And in these cases, these classifiers can be like scikit-learn or very simple logistic regression classifiers that are actually computation efficient, but the more complicated part of it is actually understanding sentiment, which the model actually does for you. So there are then maybe 3 ways of building classifiers, and this is just one of them. What are the other 2? So this example, where you give it examples and you train it to be a classifier by extracting embeddings, is commonly used by many people in the industry, but it's just one of the approaches. And let's go down to what the embeddings are again. So the baseline embeddings for a specific model are really great, but sometimes if you train the classifier purely on them, they might not get you to where you want to be. Even though these embeddings capture the semantic similarity and they're pretty accurate at that, what they're not geared to do is solve every problem you have. So you might want to fine tune them with maybe a small amount of data. Why I say this is because if you look at the diagram up there, there are like points on the left and points on the right. The points on the left are talking about like fast, late, on time, and you see that they have relative meaning, right? Even though they're not talking about the same thing, they're not obviously capturing what you want to. They have the context of time and like some effect on it on the other. And then the other one on the right is talking about the products that are sold and catalogs, and you see there is semantic similarity there. But what are you trying to look for? Say you want to look for whether or not someone is happy or unhappy with your product. And you're looking at reviews on Amazon or like maybe responses you got on your Instagram page when you're selling a product up there. So you've given examples of this exact situation, and you're able to fine tune it based on that, which means that these two orange dots that you actually want to classify as bad problems that you have versus like stuff that people are actually happy about, you're able to fine tuning for that. And when you fine tune these embeddings, the space, the latent space, or like the way the model looks at it, the numbers it uses to represent these models, they actually change and they look a little different. And this visualization kind of captures what it is. It's an example of how models could, on fine tuning, get you better results. and obviously, even without like a strong argument for it, you can see how these are able to better segregate the data into the ways that the model can actually distinguish much faster, so better quality classifiers will be able to be trained. So that approach is called fine tuning, and it's ideally one of the best ways to get you to have the perfect or like highest quality results for your use case. But yes, there's fine tuning, there is embeddings, but what if you don't really have a lot of data? What do you do there? And what's like a really cool property of large language models that allows you to build classifiers directly based on that approach? Well, I'm going to allude to that because I want to build some interest. So let's talk about semantic search. Let's get our brains activated in a different direction. Well, there are basically two ways to use language models for semantic search, and one is by looking at results and ordering them differently. So this is like re-ranking, or a way for you to say that these results are more important and more geared towards what the user is looking for, and the other results aren't. So you reorder them that way, and you populate maybe the first page of Google with better, more relevant results, and the last page with like stuff that you don't think is as important. And the last part is like dense retrieval, which is a form of having you look at like archive document embeddings, and you query for them, but you're not getting results that need to be ranked. You're finding the results and ranking them as you do. So like I mentioned, there's similarity by looking at these numbers and trying to find which numbers are closer to the other. So you can use like cosine similarity or mean square distance to kind of get the values that are closest to the one you're looking for, and say that this semantically means something closer to what the user said, so this should be ranked higher. And you rank them based on this form of dense retrieval. So if the customer, for example, asks a question, you can find out which is closer to it and then use that to kind of trigger the kind of response you give back to the user. So the person is asking about, say, how much does a burger cost? You can just link them to your menu and make them do the rest. Versus if they ask for the opening hours, maybe you can just give them a summary of your hours and some exceptions for weekdays and holidays and so on. I'm going to skip that part a little bit and come back to it, but I'm going to talk about text generation now because that's important to the last form of classification, and also a variety of problems that result or help you solve issues that aren't really obvious to people. So what is text generation? As I said, it's a form of having the model predict the next word or set of words or tokens based on word it's already seen. So you could get the model to predict content purely based on nothing, and basically tell the model that go free, roam your world, and just generate a bunch of content without any prompt or without any hint of what to do. And we give you good results, but you ideally want to tailor this model to generate content specifically for use case, and that can be different based on what you want to do. So for example, as I said, you could just generate content based on a sentence before and predict your sentence or paragraph, or you could get it to look at content and summarize it, which is really cool. Or you could get it to paraphrase a specific paragraph so that you can use it without getting caught for plagiarism, and I didn't recommend that. The last part obviously is really cool. It's also like extracting information, and it's kind of similar to the example I showed you before, where when you search Google, you're able to like look at 5 results and get content inside that, but don't just send that page as a result to the user, but get the important information out of that and display that to the user in a short, precise format. So then here's how we get to the last form of classification. It's few shot classification where you give the model maybe a couple of texts. So for example, you give it a prompt of like oranges are colored orange, lemons are colored yellow, roses are colored, and leave it blank, and the model will predict red. And that's how this few shot thing works. And we don't really train like a complicated classifier, but you prompt the model into understanding what you're trying to do, and it predicts a class based on that, which is fascinating, and it's one of the emerging properties of large language models, which allow you to do things that you probably weren't able to do in the past. I've talked a lot about prompting, and I feel like I might have confused you all into thinking that you're going to have to teach the model everything you need to do, but in one way, in one sense, it's kind of right that you do need to tell the model what you need, because the model has no idea and cannot read your mind. So prompting and prompt engineering is a new paradigm where you basically, in the way I think of it, is you code and tell the model what to do, but instead of writing Python, you do it in English, which is really cool, because you don't have to learn any programming language. You can just prompt the model and teach it to generate the content that you like, but you need to follow a set of rules to get the best quality performance out of it. So in the examples that I shared before, I also mentioned summary. And one way to do this, and I'm not recommending this is the best way to do it, but one way to do this like really quickly and without any complication is to basically give it a paragraph and say in summary, comma, and ask it to predict the next. Now, obviously, because you said in summary, comma, the model is understanding that you want to summarize the content above it. And it gives you a fairly good summary of it. And I'm not going to argue about what makes a summary good or bad, but it is workable. And it's maybe not the best approach, but it gives you something good. And in many use cases, it might just be enough to do what you want to do. But like I said, the model can generate content when you prompt it. It can't read your mind. And I think that's coming to a point where I want to warn people that large language models aren't sentient. So what they are effectively is they are models with the capability to have narrow intelligence in specific domains, or have the ability to get you the information you want, given that you engineer them or push them in the right direction. This picture over here is from Hitchhiker's Guide to the Galaxy, and the answer that we want is probably to the question, what is the answer to the ultimate question of life, the universe, and everything? Anybody know the answer to this question? 42, right. But obviously, the entire point of 42 was the fact that it does not make sense, right? This is not trained to understand life. And it looked at a bunch of data, crunched numbers, and it did something very similar to what we do with large language models, right? You gave it access to data, it looked at a bunch of data, and it was able to understand a lot of it. But for questions like this, it's really not geared to answer those questions for us. I've talked about prompt engineering, and I've talked about how it can get you to generate really useful content. But the one thing that I would say is a pro tip when you're generating content from large language models is to basically generate multiple generations so that you get different responses and then pick the best one out of that. But what does it mean to generate multiple responses? Why does the model not generate the same? There's a parameter called temperature that people refer to in the industry. It's a way to kind of tell your model about how random you want your answer. And one way to actually get this result is by tuning that parameter and saying that, okay, I want like more randomness or less randomness. And what that introduces is basically some kind of noise, which is greater noise or no noise or lesser noise, to tell the model that these are the generations you want to make, and depending on the noise and like your random that you introduce to it, you can actually get different content, which then brings me back to the point of like, how do I really know when one answer is better than the other? Do I have to manually sit there and vet the model and see that, okay, this particular generation that I got for this use case is great and I can pass this on to my user, or this generation is lousy and I shouldn't? Well, if you look at a couple of candidate outputs that the model predicts, one of them is going to be better than the other, and the way to do that is to basically get a likelihood score, and that's one of the outputs that the model allows you to get. It's think of it as a way for you to say which of this content has the most likelihood of naturally occurring in language according to the model's perception of it, which means that which of this is actually most coherent and less nonsensical. And then when you look at these likelihood, you can actually rank them and get the best of them, right? But maybe in some use cases, you don't want to get the most likelihood content. because that's not what you're looking for. Say we talk about paraphrasing, we talked about summaries. In this content, if the model takes the input content and just generates the same thing as an output, right? It's going to be coherent, it's going to have a high likelihood score, but that's not what you want. So you probably need to think about it a little differently. You want the model to have likelihood that is not very high, but not very low, just in the sweet spot for you to understand and get the exact answer that you're looking for, without forcing the model to generate content that is identical to what you want or completely away from what you want. And I feel like this is something that you probably want to experiment with and get closer to, but it's one of those ways for you to look at what similarity is and how to get the best content out of a GPT model. Because if you look at the first generation and it's lousy and you quit, you're losing out. So yes, there is generation and classification, and there are a bunch of data sets that actually allow models to get really valuable data from it. But think of it like this: you can generate data, right? So if a large language model is there and you have a bunch of examples, you can actually get it to generate more examples. That could be useful to get a lot more data to get your classifiers trained better. And obviously, there's an inherent bias that comes in, and I want to warn people that text models aren't away from bias, largely because they're trained on content that we've written as humans. So human bias can inherently make its way into these models and affect your classifications. So you might want to take certain steps to avoid that from happening. But it's still a neat way for you to get more data and augment your model performance very easily and very cheaply. So for example, there are prompts that actually generate content about specific kind of people and specific classes. And these models can obviously have inherent biases. So what's the right way to do this? Why do you want to, in one way, babysit your model when it ships out there? It's because in many ways, generating content out of models is going to be done by noise and randomness. And there's always this randomness of it getting inherent or negative bias that is from the data, even if you try to filter out all the data from it, right? So you can tell me, okay, then don't train on bad data, right? And I wish it was that easy, and I wish it was that simple for us to do this in the industry. But there are two problems. If you take out all the bad data of the internet and assume that you know the definition of bad data and have like a metric to say that this is good and this is bad, you can still have a lot of loss of information. So for example, if the model never sees something bad, it never truly understands what is good and what is bad, and it's never able to distinguish things like toxicity and semantic meaning and so on. So I'd argue it's important for the model to see all data, just like us, but then build an understanding or be kind of babysit or urged to distinguish or generate things that are good. And then again, we come back to generation and semantic search, but think of having ways to generate similar content or questions to questions that are already in existing websites and augment that to train better models. There's a model called T5 out there that is really useful for summarization and transfer and so on, but what also is really geared towards that probably some other models like BERT or GPT aren't, is the ability for it to take a specific question and mold it into something that's exactly like it, but slightly different. And I know that doesn't really make sense, right? So one of the use cases that I talk about is summarization, where you can take a model and have a bunch of content coming into it, but it can summarize that content and give you a response, but keep the semantic meaning of it, right? So it's doing that entire summarization in one step, but instead of taking like a prompt in to engineer it, it's prompt in, prompt out, right? We come back to similarity and summarization in a bit, but when you're looking at questions and getting answers to specific documents and semantic search, another really good way to do this is to take a prompt of a question that the user asks or a document where he's asking a question, and then compare that question that is being generated based on that document to a bunch of generated questions already existing. So what this does effectively is a way for you to take a question a user asks on a bunch of data on a website or a document and so on, and get the closest question that's already answered in your corpus to the question that he's asked. So you're kind of mapping a question he asks to a question you already have an answer to, and ranking it based on likelihood, and then getting the answer to the user. And this is great, right? Because effectively it means that any website can have its own Q&A bot without a lot of maintenance or overhead and it learning again from any data you have. But we've talked about like the ability for the model to understand and express information, but we haven't really talked about how the model is able to do it and how you can effectively engineer this model to maybe more visually describe or more expressively describe what its thought process is. So I'll give you an example. Let's make the model do a little math, right? And you can say like, well, it's not trained to do math, but that's one of the emergent properties, right? If you teach the model a logic or a workflow, it will try to mimic that workflow and try to do something similar. But instead of just making it do math, let's make it explain the math that it's doing. So an example of this is, say Roger has 5 tennis balls and he buys 2 cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he actually have, right? And that's the prompt you've given. You've also prompted as the answer to 11. Now let's add another question. So apart from the prompt that you've given, you added a question that you actually want the model to predict the answer of. So the cafeteria has 23 apples. If they use 20 to make lunch and I bought 6 more, how many apples do they have? Well, I'm not going to make you do the math, but I make you run through what the answer to the model exactly is. And the model is going to help on actually explaining that. Before I dive into the actual answer the model gave us, one of the ways to do this and one of the really innovative technologies to do this was this model that actually did scratchpad prompting, where you trained the model on data that actually explained its workflow, kind of like a stat space. And the model was able to keep track of these intermediate representation, computation, or text to get to the final answer. So the one thing I'd want is the fact that these models, they don't have a very great memory, right? So they live in context and they pay attention to certain details. But if you want them to pay attention to other details and express themselves, you might want to ask it to take it step by step. And when you're taking it step by step, it will predict something similar to this. If you start with the 23 apples and you use 20 of them to make lunch, you'll subtract 20. You buy 6 more, so adding 6, and then it breaks down the calculation, right? But apart from the chain of thought, the scratchpad is actually pretty useful because it's able to give you current tally. It says that, okay, we have 23 apples in the starting. We take away 20, so we have 3 apples, and we add 6, so then 9. And what this allows the model to do is kind of have like a way to talk to itself, tell itself that, hey, remember XYZ happened 2 steps back. And this way of like building memory or a scratch space in the model can actually help it solve complicated problems that it wasn't able to solve prior to this, which I feel is very fascinating but also extremely powerful. Let's talk about text processing pipelines. We talked about how the model can do semantic search and answer questions, but what we haven't talked about is like how this entire process would work in a specific industry case, right? So the customer, say for example, sends a message, and I've talked about this a couple of times. You're able to classify it to be a return or not, and then after that you'll be able to classify, okay, was the person who's returning the product happy with the product or not? And then you search for the FAQ and try to find out like if the answer to the problem he's already seeing is answered by that company or the website or reviews or similar issue in the past, and then tell the user that, hey, you want to return the product, great, but one of the ways to return the product or one of the workflows that you can follow to return it is maybe like, okay, go into the your goals or Target or some other place to return this product, and maybe because you're close to one of them, you'd prefer that. Another really cool example and one of our co-founders actually created was a way to do something very similar to the example I showed in starting, where like you asked a question and he was able to look at a website or Google and get results to you, but in a very direct and concise manner. You basically do something called semantic or grounded QA, where instead of just asking it an open-ended question, you ask it questions specifically geared to a website, and you look at the results of the website, and then you take the website's input result as a prompt and make a prediction based on that. So think of it as a question that maps to a specific website. You do semantic search and get to a specific result, but instead of just throwing that result in the user's face, gear that result into a form that answers the question better. So rewrite it in a way. And that's done by a text generation model, but then give that output to the user. For example, if I ask the question like, where is PyData happening in New York, it could give me the entire line about the PyData conference in 2022 is happening on XYZ date and this time, etc., but I don't care about the extra information. It will distill down specific information I require and give me that line. Maybe I want the address, maybe I want the name of the office or building that it's in, and it will give you just that, which is really cool. And I know we're running a little early, but I have a demo to show you also. Let me get through the summary of whatever we covered before I dive into that demo.
It's 12:30, so technically it's lunchtime, sorry.
No, you're good.
But yeah, it's going to stay for a demo. One's going to be long for lunch anyway, so they might not even have it all out yet. So yeah, this is pretty interesting.
All right. how many of you want to go for lunch? Do we want to get question answers done right now and then proceed to the demo, or? All right, cool. So yeah, we summarized what all we covered. We talked about classifiers, we talked about semantic search, we talked about text generation, we talked about different ways to build classifiers and how you can use them for different settings and how they work. But also talked about embeddings. How do you put in a similarity, a way to visualize them and get like a visual understanding of what the model is thinking and understanding. We also talked about input prompts and how models can generate text and how to gear that text to what you want, but also get multiple generations and pick out the best quality of the same. We talked about how both embedding models and text models are able to do things that are beyond just taking out embeddings, but also empower other models to do these things. And we talked about how fine-tuning actually gets us better results and helps us get results geared to a specific area that we're looking for, and basically adapt to a specific domain. And again, I'd like to thank you for slides. You can visit cohere.ai to actually go to a very neat playground that will leave open right here. But it's effectively a way for you to go and play around any of these use cases that I talked about and get a quick demo of us, and then maybe use that data to build something neat yourself. This is probably too small for you. So I gave it a prompt about, here are the things that I allowed at the PyData conference, and I predicted 100 tokens. And this is what it ended up predicting. I like the wide variety of talks, which is extremely beneficial for the PyData crowd. The fact that there were a lot of beginner talks, the fact that we could easily talk to a lot of people, the diversity of talks, and the fact that I see a lot of talks with so many different topics. Yeah, so thank you for the talk, and I will take questions now. Yes. Yeah, I'll leave that on for you to take pictures. All right, any questions before we go for lunch? Yes.
When you showed the visualization for the embedding fine-tuning,
yes.
Did you bring the whole model back?
So you don't need to bring the entire model back. The entire point of fine-tuning is to basically give it the baseline model itself, but then give it more input data, and it automatically adjusts the weights of these things and brings the content further away from each other. The more data you give this model to look at, fine-tune, the more better the fine-tuning will be.
But like which layers did you find? Just the embedding, or
you can fine-tune the entire model. You can also fine-tune the last layers of it. There's new technologies and techniques to actually fine-tune an additional layer on top of the model. And there are like adapters or TPU approaches, but the vanilla approach to do it is basically fine-tune the entire model. That's the easiest to implement, but like might not always be the scalable form to it. Any more questions? Yes.
What are the best practices for this kind of models in production?
Good question. So I actually focus on model serving, and I've been working on it myself. The one thing I can tell you about the fact that these models, like I say, are large, and that's not an understatement. These can be millions and billions of parameters. The best way to take these models is to not run them at full precision. At reduced precision, they take lesser compute, they're more faster, but there's a trade-off of quality. And then beyond that, there are certain times when people just jump into the largest possible model out there, and they think that's going to solve their problem, but that might not necessarily be the case. For many use cases, a smaller or a medium-sized model, which is still fairly large and much cheaper, can actually get you the results you want. But then the last form is actually, there is a huge complexity in deploying these models out there. Sometimes you can take up like really beefy GPUs out there that are expensive, and it's not scalable for you to always do that yourself, which is one of the reasons why Cohere builds the platform to like take the cost of serving these models and the pain of doing it off users. But if you want to do it yourself, there are like pointers out there in the industry where you can actually, in a couple of lines of code and a Docker image, get out these models and serve them. If you're talking about scale, that's a different problem. Scaling these models is kind of complicated, and I don't think there are many companies out there that solve the problem of deploying like billions of these models out there in production to users in low latency environments. Any more questions? Yes.
You talked about what you're actually using your infrastructure to do the downstream tasks for the language models.
Yes. Can you specify exactly which part when you're talking about?
From the beginning to the end, so how you're actually doing the fine tuning, the pre-training. You're not training the model because it'll take you months to do that.
Yes.
You're taking the existing BERT or the existing GPT.
Yeah. So think about these existing models that we talked about as like the ones we trained and we left with them as baselines, or the ones that you can get out there in the industry. A bunch of these models are actually out there, and these weights are available. These are referred to as baselines or like vanilla models. When you fine-tune these models, you can again say, like I said, choose to fine-tune parts of these models, attach several layers on top of the model to fine-tune it, or take like a distilled version of this. So like there's something called distilled BERT, which compresses the model down and so on. But you can find a way to get these models into a smaller compressible state and then focus on serving just that. And what this does is A, reduces the number of parameters if you're distilling them, or it reduces the overall time to fine tune by taking these baseline models and just modifying the weights on top of that. Or in one case also, it just ends up adding an additional layer on top of the model. So you're not fine tuning the existing model weights and messing with that. You're just fine tuning an additional layer, which is one scalable way to fine tune. And then in terms of embedding models, it's a little harder to fine tune the embedding model because if you fine tune it for a case, one advice people have and the way people do it in the industry is to fine tune the embedding model for a classification task. So if you fine tune the embeddings for a classification task and clear the embeddings for that direction, then you can use that from then on. Did that answer your question? Or is there more you need to know?
We'll forward.
Yes, we can talk after that. Alright, cool. Is there any more question? No more questions? Alright, thank you everyone.